Hi, statisticians. Welcome to section 9.1. Welcome to chapter 9. So in chapter 9, we're doing something a little bit different than what we've done before, but we are going to be using some of the same tools that we learned about in chapter 8. So in chapter 9, what we're doing is something called statistical tests. And another name for this is hypothesis testing. We are testing basically a guess that we're making about some data. So let's jump right in with a warm-up. The warm-up says, Lola is an aging miniature pinscher in Virginia who gets regular checkups. Let X be a random variable that represents Lola's resting heart rate in beats per minute. From past experience, the vet knows that X, this is the heart rate random variable, has a normal distribution with population standard deviation, so sigma, equals 12. So again, this is our population standard deviation. The mean heart rate for Lola's breed is mu equals 115 beats per minute. So this is the mean, this is the population mean heart rate. Over the last 6 weeks, Lola's heart rate has measured, and we've got 6 data values. So these are heart rates in beats per minute. The question is pretty simple on this one. Find the sample mean, X bar, for this data. And so you don't have to overthink this one. Remember, to find the sample mean, you just add up all these numbers and then divide by the number of values. So in this case, 1, 2, 3, 4, 5, 6. There are 6 of them, so this is going to be our sample mean. X bar is just going to be the sum of all of those divided by 6. So throw that into your calculator, and let's see what our sample mean is. When I put that in my calculator, I find a sample mean of 105 beats per minute. So just to point out, remember, the population mean is 115 beats per minute, and our sample mean that we just found is 105 beats per minute. So just making a quick note about this, our sample mean is maybe a bit small, is a little bit low. Lower, than the population mean. So the real question is, and the entire question in this entire chapter, is kind of about this phrase. Our sample mean is a little bit lower than the population mean. Basically, like, is it too low? Is it concerningly low? Or is this just like a normal fluctuation in the mean? If we measured it on a different week, would we get 125 beats per minute? Maybe it's 10 up from the mean, whereas this one is 10 down. So that's what we're testing in this entire chapter, is maybe our sample mean is a little bit off from where it should be. How far off is too far off? Okay, so this is again called hypothesis testing. Now, let me just give you some expectations about this chapter. One of the weirdest things about this topic is just the notation. So we're going to have some strange notation that you haven't seen before. One of the weirder things is just kind of like getting used to how to write out the work in this chapter. Okay, so again, just to summarize, typically statisticians do a couple of things. We estimate statistical parameters based on a sample, or we make decisions concerning the value of those statistical parameters, which is what we're doing now. Is it too low? Is it too high? Or is it kind of maybe a little bit off, but it's in the range of normal? This is where we're going to focus in chapter 9, and we're using a strategy called hypothesis testing. So in hypothesis testing, it's kind of suggesting it in the name, we develop a hypothesis about the parameter. Now, the parameter that we're talking about in the next 2 sections is the mean. We're going to be focusing on the mean. So we're going to be making a hypothesis about the mean, and then kind of deciding if our data supports that hypothesis or not. The first step is to establish a working hypothesis, which is called the null hypothesis. And then we'll have a second hypothesis, and that one's called the alternate hypothesis. So in every problem, we will have a null hypothesis and an alternate hypothesis. Now, the null hypothesis means that we don't do anything. There's no change. We're always going to use this symbol for the null hypothesis. So it's a capital H and then a little subscript 0. So the 0 is sort of set down and it's smaller than the rest of the text. And we read this H naught. H naught. Some people, you might read it, or some people will say it as H null, but we're going to say H naught. So the null hypothesis is H naught. Then, and again, the null hypothesis means that there's no change to our data. The alternate hypothesis, we'll just call this one H1, H, and then the number 1, H1, so H naught and H1, and again, little subscript 1, is a new hypothesis. And H1, our alternate hypothesis, will contain symbols less than, greater than, or not equal to. One of these three. It will always contain one of these three symbols. And I should have noted on the null hypothesis, H naught will always contain the equals symbol. So you'll be able to tell these apart for sure because they'll have different symbols. H naught, the null hypothesis, is going to be an equation with an equal sign. The alternate hypothesis, H1, is going to be an inequality, so less than, greater than, or just not equal to. Okay, so I know that probably sounds really weird. You'll get more used to this as we just practice. So let's get into it, and you'll see an example. A car manufacturer advertises that its new hybrid models get 47 miles per gallon. Let mu be the mean of the mileage distribution for these cars. You suspect that the mileage might be overrated. Okay, let's just focus there. The rest of the problem is on the next page. You think that they're overrating this mileage. So you think that this 47 is maybe too high. We think the actual mileage is lower than 47. We think that they're kind of inflating this number. Okay, so we think that the actual mileage is lower than 47. In other words, we suspect that they are overrating their mileage, where they say it's 47 miles per gallon. We think maybe that's a little high. Okay, so flipping to the next page, the question is, what should we use for H naught? Now, H naught is the null hypothesis, and the null hypothesis, first of all, represents that there's no change. We don't change anything. And also, it's always going to have an equals sign. So there's no change, and we just say the mean equals something. So our null hypothesis is going to look like this. And again, the notation is something to get used to here. We'll say H and then little subscript 0. So H naught, and then you put a colon. Always starts like this, H naught colon. And this is basically a statement of my null hypothesis is. And now I'm going to write an equation. Remember, the null hypothesis always has an equal sign. The null hypothesis, and we're talking about the mean of the mileage, so mu. Our null hypothesis is that mu equals 47 miles per gallon. Our null hypothesis is that there's no change. They say it's 47 miles per gallon. We say, okay, no change. It's 47 miles per gallon. We used an equal sign. We didn't change anything that they gave us in the data. Now, our alternate hypothesis, H1, is going to be a little bit different. Similar notation though. So now we're going to use a greater than, a less than, or we can just say a not equal to. And so going back to kind of what we talked about in the problem, we suspect, and I can phrase this deliberately and say, we hypothesize that the actual mileage mean, the actual mean mileage is lower than 47%. And so when I'm reading this, lower than, I can kind of read a less than symbol there. So my null hypothesis, my alternate hypothesis, H sub 1, alternate hypothesis is that the actual mean is less than 47 miles per gallon. So this is if we don't do anything, but this is kind of like, we suspect this might be a little bit lower. Okay, so now we have our hypotheses written down, our null hypothesis and our alternate hypothesis, and we have to test these hypotheses. So there are a couple of different tests that we can perform. We categorize the tests as left-tailed, right-tailed, or two-tailed, according to, well, just the symbol. If it's a less than symbol, then that is left-tailed. So left-tailed goes with less than. Right-tailed goes with greater than. So right-tailed goes with greater than. We're saying that we think our mean is larger, so it's on the right. And then lastly, two-tailed is that not equal to. If you see a not equal to symbol, that's a two-tailed test. So going back to the one that we just did, we're hypothesizing, our alternate hypothesis is that the mean is less than 47. Well, less than is a left-tailed test. Don't overthink this. Less than means left-tailed. Greater than is right-tailed. So this type of test would be a left-tailed test. Left-tailed. Okay, so now we've got our test categorized. Left-tailed, right-tailed, or two-tailed, just based on the symbol. Like, of this entire section here, if you just memorize that, you're golden. Left-tailed goes with less than, right-tailed goes with greater than, two-tailed goes with not equal to. So now that we have our hypotheses and we've categorized our test, we can test them basically by using the same tools that we've been doing. We're going to convert our value to a z-score using this formula, and then we'll test it using something called the level of significance. Okay, and I'll get to that in just a few minutes, but we're kind of like building up to the entire process. Okay, so I just want to point out really quick, hypothesis tests, given that X is normal and sigma is known, if you think back to chapter 8, when we were making confidence intervals, remember, this is pretty friendly. A lot of times we don't know our population standard deviation, and we're actually going to get to that in the next section. What happens if you don't know sigma, you only know S? And you can maybe think back to chapter 8 and kind of guess where that's going. If everything is friendly and we know sigma, then we're going to use Z. And just a little bit of foreshadowing, if we don't know sigma, then we're going to use a different distribution that you learned about in chapter 8. So you can maybe guess what's coming up. Okay, so just to summarize the process, remember this is just a fact. If X is normally distributed, then so is the sampling distribution, X bar. The sample test statistic x bar, the sample mean, has a z value given by this formula. And of course, this is in your formula sheet, where mu is the stated value that's from our null hypothesis. So you'll always have mu, that's in the null hypothesis. You will have sigma, it will be given to you in the problem. You'll have n, that's the number of data values, that's the size of your sample. You'll be given that in the problem, and you'll be able to find your sample mean. Okay, so we're going to basically do that and convert the x bar value to a z-score. So let's put this to work. Same problem from the warm-up. Lola is an aging miniature pinscher. Here she is. She's also sitting right next to me. Lola is an aging miniature pinscher in Virginia who gets regular checkups. Let x be a random variable that represents Lola's resting heart rate in beats per minute. From past experience, the vet knows that x has a normal distribution with sigma equals 12. Pretty friendly that they gave us sigma, but we'll deal with that in section 9.2. The mean heart rate for Lola's breed is mu equals 115 beats per minute. Over the past 6 weeks, Lola's heart rate has measured, and we have these same 6 data values that you were given in the warm-up. So in the warm-up, we just added all these up. The sample mean, we added them up, I should say, and divided by 6. We found a sample mean of 105 beats per minute. The vet is concerned that Lola's heart rate may be slowing. Do the data indicate that this is the case? Well, remember, the population mean is 115. Lola's sample mean for at least these 6 heart rate measurements was 105. Okay, so we can definitely say that the sample mean that we gathered is lower than the population mean. But who knows? I mean, maybe it's a distribution. It says it's normal, right? So maybe 115 is right here in the middle, like it says, and maybe this goes all the way down to like 95. I have no idea. Maybe it goes all the way up to 135. And so, yeah, 105 is like in here, but maybe it's still okay. Maybe 105 is still totally in the realm of like not abnormal. We don't know. That's what we're testing. We can definitely say it's lower, but the question is it concerningly low? Is it like the scale is off and her heart rate is down here where it should not be? So that's what we're testing. How low is it? Is it concerningly low? Okay, so let's start the process. And just to spoil the big surprise for you, every single problem in these 2 sections is going to have this exact same strategy. Like, we're always going to start by establishing the null and alternate hypotheses. We're going to convert to a z-score or a different score in section 9.2. And then we'll be able to test to see, is it too high or too low, or is something unusual here? Okay, so establish the null and alternate hypotheses. Well, the null hypothesis, remember, is that nothing has changed. So the null hypothesis is that the population mean is equal to 115 beats per minute. 115 beats per minute. The null hypothesis is always going to have an equal sign. So basically you take whatever mean they gave you in the problem and just copy that right here. Whatever they give you, population mean, just don't change it. That's your null hypothesis. Always going to have an equal sign. Now, our alternate hypothesis comes from our set of data. And since Lola's resting heart rate was a bit lower, I'm going to use the inequality symbol less than. I'm thinking that maybe her resting heart rate is less than 115 beats per minute. So I don't have, now, okay, let me just clarify this. I would never say equals 105 here because the alternate hypothesis will never have an equal sign. it's always only going to have a less than, a greater than, or a not equal to. So since we got a number that's less than 115, I'm just going to go with this one on this. And you'll see some other examples where we would use not equal to, and it'll generally be pretty clear in the problem which symbol you should use. Okay, so here's my null hypothesis, here's my alternate hypothesis. Now the second part of this is asking, are the observed sample data compatible with the null hypothesis? In other words, find the probability that the sample mean is less than, I should say less than or equal to 105. Okay, and this is coming from the sample mean that we got. So find the probability basically that this would happen. Okay, so I'm going to take this 105. I'm going to take our x bar value of 105 and convert that to a z-score. And to do that, I'm going to use the formula x bar minus mu over sigma divided by the square root of n. And that's coming from either your formula sheet, and make sure that you're using the z-score formula that's for x bar, which is different than the formula that's for x, or you can also just get it from right here. But make sure that you are using the one with an x bar there, because it's a slightly different formula with this square root of n. Okay, so to convert 105 to a z-score, I'm going to plug in my values. Everywhere I see an x bar, I will put 105. Everywhere I see a mu, that's this mu. Mu equals 115. So 115 over sigma. Well, they gave me sigma in the problem. Sigma equals 12. And over the square root of n, n is that sample size. And so because we were given 1, 2, 3, 4, 5, 6 values, that's my sample size here. So toss that into your calculator and let's round this, if necessary, to 2 decimal places like we usually do for z's. So when I put that into my calculator, I find a z-score of negative 2.04. So that's the z-score that I want to find. And since this is a less than or equal to, that's the equivalent of me finding a left area now using my z-table. So looking at my z-table, now I'm finding the probability that z, my z-score, is less than or equal to negative 2.04. This is why it's important to identify in the problem whether I'm using a left-tailed or a right-tailed or a two-tailed test. It's important that I know what kind of area I was looking for. And in this one, I'm finding a left-tailed area, so I'm just going to take that probability right out of the table and not adjust it at all. But if I were finding a right-tailed area, if this were a problem where it was like greater than or equal to, I would just have to adjust by subtracting by 1. So make sure that you're keeping track of that. We're finding left area on this one. Okay, so hopefully you've had time to look through your z-table. When I look through my z-table and find the value of negative 2.04, I see that it's associated with an area of 0.0207. So what that tells me is that there is a 2.07% chance, or 2.07, my goodness, 2.07% probability that we would get a heart rate, that we would see a heart rate of 105 or anything less than that. So let's just summarize what we know so far. We know that for all min pins, for all of these aging min pins, all these dogs, the resting heart rate, the average resting heart rate is 115. For Lola, for this dog, we found her resting heart rate to be 105. We averaged these six data values. Pretty small sample, but it said it was already normal, so it's okay. So we found an average of 105. And now, by converting that to a z-score and finding the associated probability from the table, we see that there is a 2.07% chance that the heart rate that we find would be that low, which is pretty small. That's a pretty small probability. So, what conclusions can be drawn about Lola's average heart rate? Well, I would say it's definitely slower than average. It seems like it's maybe concerningly slower than average. If there's only a 2.07% chance of seeing a heart rate that low, then she's definitely on the outskirts of the graph, right? Like maybe this is a concerning value. So the last question here, and a really important question, is have we proven the null hypothesis to be false? Have we proven it false beyond the shadow of a doubt that the average heart rate, the population mean heart rate, is not 115 beats per minute? Have we proven beyond a shadow of a doubt that her mean heart rate is for sure less than 115? And the answer is no. No. Remember, first of all, there's still a 2.07% chance that this could happen. So it's pretty low, and we'll actually talk on the next page about how low is too low. But no, we never prove the null hypothesis to be false. What we will say is that we reject the null hypothesis. We reject the null hypothesis. We never can say that we've proven it to be false. We never can say that we accept the alternate hypothesis. All we ever say, and we always use this exact language, is that we reject the null hypothesis. Okay, so now let's talk about actually on the next page we'll get to how low is too low. On this page, let's talk about the p-value. So we found what's called a p-value actually in this example. We didn't call it a p-value, but p stands for probability, and this is our p-value here. The p-value is the probability or the area that is associated with our z-score, and we'll just get that from the table. So on the problem that we just did, remember we found a z-score of, what was it, 2.04? Negative 2.04. So we were kind of looking at a picture like this, negative 2.04, and since our test was left-tailed, so less than, right? Left-tailed means it's a less than symbol. Since our test was left-tailed, we wanted to find the left area. Left-tailed test means that we're finding the left area. And so when you're finding the left area, well, the table kind of automatically gives you the left area, at least for the z-table. It automatically gives you the left area, so we don't have to do any kind of adjustment for the left area on this. We just got it right from the table, and you don't have to subtract from 1 or anything like that. If you're doing a right-tailed test, so now your test is greater than, your alternate hypothesis is greater than, well, then in that case, you are going to need to adjust your area by subtracting from 1. Because remember, the table always gives you the left area, so you'll just have to do 1 minus your table value. And that'll give you your right area. So that would be your p-value in a right-tailed test. Now in a two-tailed test, which is not equal to, your alternate hypothesis says not equal to, you're just going to take that left area, or the right area, whatever you can find, whichever area, and multiply it by 2. Because the two areas are going to be the same, so you'll find whichever one is easier and then just double it. And that would give you kind of the mirror image on the right side, and so that would be a two-tailed test. Two-tailed test, you just double your area. So don't overthink that too much. Now, let's talk again about the question of how low is too low. So when we're using hypothesis testing, there are two types of errors that we can encounter. This is going to seem really complicated, but there's only like one little part of it that you need to use. So this is just sort of a general explanation. There are two types of errors that we can make during null hypothesis or during hypothesis testing. So if your null hypothesis is true, but we reject it. So the null hypothesis is true, but we say, no, I don't think it's true. This is something called a type 1 error. And the probability of a type 1 error, probability of a type 1 error is alpha. We say the probability of a type 1 error is alpha. And that's just what this is saying. Type 1 error with probability alpha. Now, on the other hand, if our null hypothesis is false, but we don't reject it. So we say like, yeah, that seems like it makes sense. Everything seems reasonable here. This is something called a type 2 error. So it really isn't true, but we don't reject it. That's called a type 2 error, and the probability of a type 2 error is beta. But honestly, you don't really need to know much about beta. Alpha is a really important one here. Alpha also has a special name. It is called the level of significance. And basically what it does for you is give you a cutoff for the probability. So remember, on the LOLA problem, we found a probability of 2.07%, which is pretty low. But in order to be able to say it's too low, someone needs to give us a cutoff. And just as a quick example, let me look forward and see if we're going to come back to this. No, I don't think we are. Okay, so in this problem, if someone said alpha equals 1%, which is going to be a fairly common level of significance, alpha equals 1%, that's basically saying this. Here's a number line. Here's 1%. Here's our alpha. It's basically saying anything to the right, anything over here is okay. Even 2%, even though it's like pretty low, 2% is still in the realm of okay. If you get anything less than 1%, anything over here, that is not okay. So that's where you would reject your null hypothesis. Okay, so let's put that to work. Yes, actually, before we do this one, let's skip to the I really understand this problem because that's using the same example. Okay, so we'll do this in a weird order, but let's talk really quickly about I really understand this number one. Okay, so number one says a company manufactures ball bearings for precision machines. The average diameter for a certain type of ball bearing should be 6.0 millimeters, so exactly 6 millimeters. To check that the average diameter is correct, the company formulates a statistical test. First question, actually all this is asking is for the null and alternate hypotheses. We won't actually do a test quite yet. So the null hypothesis, we always use this notation, so H naught and then a colon, always starts with this. The null hypothesis, well, the null hypothesis is basically that we just accept what's in the problem, that the average diameter is 6 millimeters. So the mean equals 6.0 millimeters. There's no change. Remember, the null hypothesis is always going to have an equal sign. Okay, so you always just put mu equals blah, 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 whatever it is from the problem. Now, the alternate hypothesis, they're going to have to kind of hint to you in the problem if it's a left-tailed or right-tailed or two-tailed test. And this is that hint. An error either way, too small or too large, would be serious. So our null hypothesis, it basically doesn't want to restrict us to just a less than, not just restricted to too large, or not restricted to too small, not restricting to either one of these. This says an error in either direction would be serious. So our alternate hypothesis is going to be a not equal to. If it's less than or if it's greater than, basically if it's different in either direction, if it's different than 6 in either direction, that would be serious. So that is our alternate hypothesis. Okay, so keep those in your head, and now let's go back to the example on the previous page. We've got our null hypothesis here. We've got our alternate hypothesis here. Suppose the manufacturer requires a 1% level of significance. Now, the level of significance is just called alpha. So we're saying alpha equals 0.01 or 1%. Alpha equals 1% or 0.01. Let me just double check in your book and see if we're going to express that as a decimal. Suppose the manufacturer requires a 1% level of significance. Describe a type 1 error and its probability. Okay, well in this case, remember a type 1 error is up here in this little table. Type 1 error is the null hypothesis is true, but we reject it. So in this case, the null hypothesis is that the population mean, mu, is 6.0 millimeters. So a type 1 error is that that is true, but we reject that hypothesis. But we reject that hypothesis. Now, what is the probability of that happening? The probability is just that alpha value. The probability of that happening is 1%. The probability of this error, of this particular type of error, is 1%. That's the level of significance. That's alpha. Now, discuss a type 2 error. Well, that's kind of going the other way. So a type 2 error is where the null hypothesis is false. So in other words, this is false. The population mean, mu, is not 6.0. But we don't reject that hypothesis. We fail to reject the null hypothesis. And the probability of that is something called beta, but again, you don't really have to worry about that one too much. We just really care about alpha, the level of significance. So to conclude a statistical test, and I already mentioned this on the Lola example briefly, if the p-value, if the probability that you find is less than or equal to alpha, then we reject the null hypothesis and we say that the data are statistically significant at the level alpha. So to draw you that number line again, whatever they give you for alpha, now who knows what it is? It could be 1%, it could be 5%, it could be 25%, I don't know, whatever. They have to give it to you in the problem. The problem is always going to say the level of significance is blank percent. They have to give it to you. Whatever this is, if the probability that you find is on this side, anything greater, then you do not reject, you do not reject your null hypothesis. Anything over here, anything greater. So if your level of significance is 1%, then anything greater than 1%, even that teeny tiny 2% probability that we found on the Lola example, it doesn't matter. You do not reject your null hypothesis. Now, back in that example, we didn't have a level of significance, so we weren't doing this precisely there. Anything less than your null hypothesis, anything less. So if you find a probability or a p-value, anything less than whatever your level of significance is, then you reject your null hypothesis. Anything over here. Okay, so let's put this all together in problem number 2 of the I really understand this. So this one is like full detail, start to finish, the entire problem. The EPA has been studying Miller Creek regarding ammonia nitrogen concentration. For many years, the concentration has been 2.3 milligrams per liter. However, a new golf course and new housing developments are raising concern that the concentration may have changed because of lawn fertilizer. Any change, increase or decrease, that's an important phrase to tell you if it's a right-tailed, left-tailed, or two-tailed test. Any change, an increase or a decrease, in the ammonia nitrogen concentration can affect plant and animal life around the creek, so we're concerned about a change in either direction. Let X be a random variable representing the ammonia nitrogen concentration and assume that X has a normal distribution with sigma population standard deviation equals 0.30. Now, it's important that they said this normal distribution thing because this is a pretty small sample. It's definitely not greater than or equal to 30, which is, remember, that's kind of like that cutoff to make up for not knowing if your sample is normal or if it's not normal. Recently, a sample of 8 water tests from the creek gave the following X values. So these are the ammonia nitrogen concentrations. And remember, before this golf course, it used to be 2.3 average. The sample mean from this sample is 2.51. Now, quick note, they didn't have to give this to you. You could have added these up and divided by 8 and gotten this, or if it was more than 8, if it was anything a lot more than 8, you could just put these in list 1 and then do your one variable statistics to get a sample mean. It's friendly when they give you the sample mean, but they don't have to give you the sample mean. You can find it yourself. We would like to construct a statistical test to examine the claim that the concentration of ammonia nitrogen has changed from 2.3 milligrams per liter in either direction, right? Increase or decrease. Use the level of significance alpha equals 0.01. First things first, what is the null hypothesis and what is the alternate hypothesis and what is the level of significance? Okay, so the null hypothesis, H naught, colon, is that nothing has changed. So we just take the mean that they gave us in the problem, 2.3, and we say that's what it still is. Mu equals 2.3 milligrams per liter. Nothing has changed. Our alternate hypothesis, H sub 1, now is that something is different in the problem. And they'll have to tell us, are we testing that it's higher or lower, or does it tell us in either direction? And this says any change, increase or decrease. So that tells us this is a two-tailed test. We don't want to restrict to greater than 2.3 or less than 2.3. We're just saying if in either direction it's not equal to 2.3 milligrams per liter, that is a problem. And the level of significance on this one is 0.01. So alpha equals 0.01. Again, they just have to give this to you in the problem. So you never have to come up with this value. They'll have to just hand it to you. Is this a right-tailed, left-tailed, or two-tailed test? So again, don't overthink this part. Left-tailed means less than, right-tailed means greater than, and two-tailed is not equal to. And so for this particular problem, it says not equal to, and so this is a two-tailed test. This is a two-tailed test, just because it says not equal to, that's it. If it was greater than, it would be right-tailed. If it was less than, it would be left-tailed, but it's not equal to, so it's two-tailed. Now, this next question might seem a little bit weird, but it's sort of hinting at what we're going to get to in section 9.2. What sampling distribution should we use? Well, same decision tree that we did in chapter 8. Do we know sigma? Because we do, we're going to use Z. And you can probably see where this might be going in section 9.2. The answer is going to be no, and we're going to use the student's T distribution. In this case, since we haven't gotten to that yet, and we do know sigma, the sampling distribution that we're going to use is Z, the standard normal. And that's true because we know our population standard deviation. We know sigma. Okay, what is the value of the sample test statistic? This phrase, sample test statistic, just means Z. They use this sort of general phrase because they don't want to give it away in the problem which one you're using, because you ultimately will have to decide if you're using Z or if you're using T. So they're not going to say what is the value of Z or what is the value of T. They're going to say what is the value of the sample test statistic, and that's because you are supposed to decide which sampling distribution you're using, so whether you're using Z or T. Now, convert the sample mean X bar to that standard Z value. Okay, so we're using the formula Z equals X bar minus mu over sigma over square root of n. And we'll have all these values from the problem. So X bar, they gave us right here, 2.51. Minus mu, that one comes from your null hypothesis, 2.3. Over sigma, I believe they gave us sigma in the problem. Yes, sigma equals 0.3. Over the square root of n. N is our sample size, and in this problem we have a sample of size 8. We have 8 data values. So throw that into your calculator and round it to 2 decimal places. When I round it to 2 decimal places, I find a z-score of 1.98. Actually, I should put approximately because I had to round it. Approximately 1.98. So there's my z value. Now, draw a sketch showing the p-value area on the standard normal distribution and find the p-value. So here's what that's asking. Let's draw a normal distribution. That one's a little bit wonky, but that's okay. Remember, on the standard normal, the mean, the middle of the distribution, is 0. And our z-score that we found was 1.98. So on my standard normal curve, I'm just going to sketch this anywhere because I don't know exactly what this one looks like, but here's 1.98 on here. And so if I find, actually the area that would be pretty easy for me to find on this one is the right-tailed area after 1.98. So I'm going to do that. Okay, so in my table, when I look at a z-score of 1.98, I'll say this, the left area is, I'm looking in my formula sheet, okay, 1.98, 0.9761. 0.9761. Well, because 1.98 is on the right side of the curve, I'm going to find the right area by just doing 1 minus that. So this will find the right area. 1 minus 0.9761 is 0.0239. 0.0239. So that tells me that this right tail, just this particular right tail, is 0.0239. Okay, now there's really not any more area work to be done because remember, everything on the standard normal is symmetric. That's one of the reasons that we like it. So that tells me if I just mirror this whole thing, even this 1.98 value, on the other side, so negative 1.98, just flip it right over. Flip it over here. The left tail area on this side is also 0.0239. And the reason that I'm finding both of those areas is that remember, we identified in part B that this is a two-tailed test. And when you're doing a two-tailed test, that means that you want to find the right area and the left area both. You want to add these two areas together. That's what a two-tailed test does. Okay, so I know that the right tail is 0.0239. I know that the left tail is 0.0239 also. And so our p-value for a two-tailed test is just both of those together. So I'm just going to double 0.0239. And so when I double that, I find 0.0478. In other words, a probability, that's what the P stands for, probability of 4.78%. Basically a 4.78% that these 8 data values would happen given that the mean is 2.3 milligrams per liter. So pretty low probability. There's like just a shade under a 5% chance that our data kind of makes sense with that 2.3 population mean. However, even though this is a really small number, remember the level of significance that we were using was 0.01. So if I'm drawing out that number line again, alpha is like 1%, right? So 1% or 0.01, well, we found a 4.78%, so well in this range, 4.78%. And anything that's to the right of your level of significance, alpha, we do not reject your null hypothesis. You do not reject your null hypothesis. So what is your conclusion? Typically the wording is, we fail to reject. So sounds like a little bit of a double negative, but that's what we say. We fail to reject H naught. We fail to reject our null hypothesis. And that's true because the p-value that we found is greater than alpha. It's on the right side of that number line of alpha. You don't really have to write this part, you can just envision it, but it does help for me to show my work like this, so I usually write it. But we fail to reject H naught because our p-value is greater than alpha. Okay, so I've already kind of like hinted at what we're doing in the next section. In 9.2, we're basically going to be following the exact same steps again, but we're going to be following a different branch. Do we know sigma? No, we're not going to know sigma. And so in section 9.2, we're going to do all the same stuff, but we're going to go right back to that student's t distribution. So I'll see you then.